we have on the itinerary for today is to start our discussion on power in three-phase circuits. And after reviewing the syllabus on yesterday, Monday, I have discovered that we will be finishing this class up with regards to lectures on Thursday. So what I'm going to do is either Thursday or Friday post your exam 3, and then it will be due at 5 p.m. on August the 13th, which is literally the last minute that the quarter is open technically. That's also when your homeworks and all that kind of good stuff are due. So I will be around all of next week if you have any questions about anything, but we're not going to have like any official class meetings. So you can either shoot me an email and schedule an appointment, or pop in over Zoom or whatever, or try to randomly catch me in my office whenever I feel like being in there. So, all right. So, yeah.
So the project methods.
So I kind of forgot to do them. So what's going to happen is you're going to get full credit for all of the work that I've asked you to do, which is none. So, yeah. So my bad, but I guess you get like a free half a letter grade or something like that. I don't think anybody actually needs it, but it is what it is. It slipped my mind. And at this point, I think it's too late to make you go back and design op-amp circuits and crap like that. So it's easier to just give you some points and say that I'm a bad teacher. So, all right. So the first thing that I want to talk about is instantaneous power. And instantaneous power is a time domain quantity. So if we have a Y connected load, and anything I'm about to do here is also valid for a delta connected load. Terminal A, B, sorry, they should be capital letters because they're on the load side. We would have some voltage VAN, some voltage VN, and some voltage VCN, where I'm assuming this load is connected to some external source and all that kind of good stuff. We'll also have our phase currents, IBN, IAN, and ICN. So that's what it looks like in the frequency domain. In the time domain, actually, I'm assuming an inductive load here, because the overwhelming majority of the time that will be the case. So I have some time domain voltage signals, and then obviously some time domain current signals as well. where our time domain signals will be something like this. Let's say that VAN of t will have some magnitude Vm cosine omega t plus 0 degrees volts. Actually, I take that back. Plus theta v volts. And corresponding current IAN of t will be Im cosine omega t plus theta I amps. Then we could say that VBN, if we have a positive phase sequence, will be the exact same thing as VAN, except with a phase angle of a negative 120 degrees tacked on. So Vm cosine omega t plus theta v minus 120 degrees volts. And our current will follow suit. And then finally, over our C phase, sorry, my hand is cramping up and my handwriting is getting more awful than usual. We'll have omega t plus theta v minus 240 degrees volts and a similar current. That unit on that current should be amps. All right. So the instantaneous power absorbed by the A phase, so let's call this PA, is just going to be VAN of t multiplied by IAN of t. And this is going to look extremely similar to when we just did the instantaneous power absorbed by a generic load for a single phase circuit, right? So we're going to use that trig identity. Let me write it over here. Cosine angle 1 times cosine angle 2 is going to be 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. So that's going to look like 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. Following suit for the B phase, we are going to have 1/2 Vm Im cosine so I'm going to have theta v minus theta I here again for the DC portion. So I want to look at that, right? So what we're doing right now is we're taking this part and then subtracting this guy from it. So we're going to have omega t minus omega t, and then we're going to have negative 120 degrees minus negative 120 degrees, giving us 0. So all we're left with is the theta v and the theta I. When we do the part where we combine them, 1/2 Vm Im cosine twice omega t plus theta v plus theta I minus 240 degrees. And similarly, across our C phase, we'll have 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I minus 480 degrees. But I'm going to express minus 480 degrees as minus 120 degrees because they represent the same angle, right? So 480 is 360 degrees away from 120. So I'm going to call this minus 120 degrees. So when I add all these three guys together, I'm going to call this P three-phase as a function of time. What I get is 3/2 Vm Im cosine theta v minus theta I, and all of the AC terms exactly cancel each other out. As we showed on, I guess it was last Thursday, if we have three quantities, all 120 degrees out of phase with each other, when we added those together, it equaled to 0. So that's why all those AC terms cancel. So the instantaneous power absorbed by a three-phase load, doesn't particularly matter if it's a Y load or a delta load, but I'm just deriving it here for a Y load, is constant. That is phenomenal, okay? It maybe seems a bit counterintuitive because there are 6 sinusoidal signals varying in it to get that power, but all of the AC terms cancel each other out. And so we find that the instantaneous power is exactly the same as the average power. So this is one of the biggest reasons that three-phase systems are used to run induction motors, because if we're delivering a constant amount of power to it, then the motor is experiencing a constant amount of torque, which means it does not suffer from mechanical vibrations due to the power surging in and out, which means that they last longer. There is a very good reason why in our power lab, which is pretty much directly behind us, some of our rotating electric machines in there are pre-World War II, and they still work. And it's because they're three-phase motors. And so unless you actually go in there and start messing around with stuff and causing vibrations, which would then incur material degradation, the things will effectively run for pretty much ever, as long as you keep them properly cooled. All right, so instantaneous power is taken care of. Now let's talk about complex power. Excuse me. So I'm going to take my same Y-connected load. A N terminal B and terminal C. Define my voltages and all that kind of jazz again. VAN, VN, CN, currents, IAN, IBN, and ICN. So if I wanted the complex power absorbed in the A phase of the load, let's call that SA, that would be my voltage VAN times the complex conjugate of my current IAN, which I can express as the magnitude of VAN times the magnitude of IAN with an angle of theta VAN minus theta IAN, or alternatively, the magnitude of VAN times the magnitude of IAN with an angle of theta ZY, right? Because the angle of the impedance will always be the angle of the voltage minus the angle of the current. For the B phase of my load, I'll have VBN times IBN conjugate, which would be the magnitude of VBN times the magnitude of IBN times angle theta ZY again. And since I know that in a balanced three-phase system, the magnitude of the voltages across the load have to be the same, and the magnitude of the phase currents have to be the same, I could express this guy as VAN, magnitude of VAN times the magnitude of IAN with an angle of theta ZY as well. And so should stand to reason that the complex power absorbed by the C phase is actually going to be the exact same thing. So VCN times ICN conjugate looks like the magnitude of VAN times the magnitude of IAN with an angle of theta ZY. So from this, the total complex power would be SA plus SB plus SC is just going to be 3 times SA. Because all of the phases are going to absorb the exact same amount of complex power. So what I'm going to do now is I'm going to split this guy up a little bit. I'm going to call this 3 VP IP angle theta Z. VP represents the phase voltage, or the magnitude of VAN, and IP represents the phase current, or the magnitude of IAN. So we now have an expression for our complex power in terms of our phase quantities. All right. So we know that there is a relationship between the phase voltages in a Y-connected system and the line voltages in a Y-connected system, where they are related by a factor of square root of 3 angle 30 degrees. I hope at this point we've beaten that practically to death. Okay. So I could say alternatively that this is going to be square root of 3 times square root of 3 VP times IP with an angle of theta Z, where square root of 3 VP represents VL, the line voltages. So I'd have square root of 3 VL, and in a three-phase system with a Y-connected load, what's the relationship between the phase currents and the line currents? Let me draw a little picture here real quick. Know that we've talked about this explicitly. So really, this is all I need to look at. So I have a line current, IAA, flowing through my transmission line. And then I have a phase current, IAN, flowing through the load. So in the A phase, what's the relationship between those two currents? They're the exact same thing. So erase all that junk now and say, since IP and IL represent the exact same quantity, I now have an expression utilizing the line quantities. So this would be the magnitude of VAB, and this is the line current, or the magnitude of IAA. So I'm going to put those guys in boxes. Would these relationships hold for a delta connected load? Yes. In a delta connected load, the line voltage and the phase voltage are the same thing, right? But if we look, if we look at the relationship between the line current and the phase current, though, we should see that that's where that extra square root of 3 term is going to come from. So let's say that I have, here's my transmission line, having a line current of IAA. Here's the delta. This is my B terminal. And then over here, here's my phase current, IAB. Here's my phase current, IAC. So I could say that IAA, my line current, is equal to IAB minus IAC, which would be IAB times 1 angle 0 minus 1 angle negative 240, or IAB root 3 angle negative 30 degrees. So there's still a square root of 3 relationship. Now it's the conversion between the line current and the phase current. So even though we derived these explicitly for a Y connected load, they're absolutely valid for a delta connected load as well. So we now can calculate complex power for our loads on a line quantity basis and a phase quantity basis, which means we get to kind of mix and match and choose how we go about calculating our power quantities. So delete that because it's not terribly important. All right, so we now know what our complex power is. So Now we need to figure out our real power, right? So let's say our average power, P three-phase, is going to be the real part of 3 VP IP angle theta Z in terms of phase quantities, or the real part of root 3 VL IL angle theta Z, or my line quantities. So what should the real part of this guy be? So without the angle, that's just the magnitude. So that's not the average power, that's the apparent power, which will cosine, exactly right. So 3 VP IP cosine theta Z, or root 3 VL IL cosine theta Z. So the real part is the cosine, the imaginary part is then the sine. So our reactive power Q three-phase is going to be the imaginary part of 3 VP IP angle theta Z, or the imaginary part of root 3 VL IL angle theta Z, which would be 3 VP IP sine theta Z, or root 3 VL IL sine theta Z. Our apparent power S three-phase is just the absolute value of 3 VP IP angle theta Z, or the magnitude, which would just be 3 VP IP. And in terms of my line quantities, be the magnitude of root 3 VL IL angle theta Z, or root 3 VL IL. All of these are coming from our steady state sinusoidal power relationships, except that since our load is now composed of 3 impedances, we have to multiply by a factor of 3. It's literally nothing remotely new. Our power factor PF three-phase will be, by definition, our average power divided by our apparent power, or simply cosine of theta Z. All right, let's work a couple of example problems, and then we will wrap up for the day. Thursday will be power factor correction in 3-phase systems, and then we're done. Unless you guys have any questions, in which case I am happy to answer them. So let's say that we have the following circuit T. And lowercase n, and let's say that this guy is 40 millihenry. And I want us to determine the total reactive power absorbed by the load the average power per phase absorbed, by the transmission line and C the power factor at which the source supplies power. So the three quantities that I am asking about are all RMS phasor domain quantities. So the first thing that we're going to have to do is convert our time domain circuit into an RMS phasor domain circuit, right? So if VAN of t is equal to 100 root 2 cosine 120 pi t volts, what is our RMS phasor voltage VAN? Yeah, why wouldn't it be? Right. So to get to a phasor, we would have 100 square root of 2 angle 0. To get to an RMS phasor, we would divide that magnitude by the square root of 2, leaving us with 100 angle 0 degrees RMS. What should the impedance of our wire be? So 10 plus J times 0.005 times 120 pi, which I get to be J 1.88 ohms. Similarly, the impedance of our Y connected load would be 40 times J times 40 plus J times 120 pi times 40, or 40 plus J 15.08 ohms. And so now we have enough information to construct our single phase circuit and analyze this guy for the quantities that we're looking for, right? So our single phase circuit, 100 angle 0 degrees. Here's lowercase a, here's lowercase n. I have this impedance, EW, which is 10 plus J 1.88 ohms. Here's uppercase A. Here's our impedance ZY, which we know to be 40 plus J, 15.08 ohms. Uppercase N, short circuit. So part A, we want the total reactive power absorbed by the load, right? So I would argue that we're going to need the voltage across the load and the current flowing through the load in order to get that. Now, technically speaking here, because we're dealing with a single phase equivalent circuit, we could actually go back to all of those alternative relationships that we developed for steady state sinusoidal circuits, where if we know only the current and the impedance or only the voltage and the impedance, we can actually get the complex power. And then from that, we could determine the reactive power. So we can fall back on those simple single phase quantities and remember that we have to multiply by a factor of 3, or we can use our 3-phase relationships, which already have that factor of 3 built in. It's really just whichever relationship you're more comfortable with using. That's kind of the beauty of a single phase equivalent circuit, is that we get to go back and treat everything like a single phase circuit, where we've now spent between circuits 1 and circuits 2 roughly 6 weeks on that crap. So it should be pretty beat into your head by now. All right, so which way would you guys prefer? A single phase look at this thing or the 3-phase perspective? All right, so what do we want, voltage or current? Which one's easier? They're both trivial, sure. So the current, so I am going to do, so let's say specifically the phase current IAN here. So we could say that IAN is equal to 100 angle 0 degrees volts RMS divided by the total series impedance seen by our source, which in this case would be, oh, I don't know if I can add those two numbers in my head explicitly, so I'll write them out. 10 plus J 1.88 ohms plus 40 plus J 15.08 ohms, which I get to be 1.894 with an angle of, what the heck just happened? Give me just a second to remember how to change the view to look at just one page. Maybe I hit this. And my hand grazed something. I apologize. Negative 18.742 degrees. My stylus will write. Amps. S. So from this, the total complex power, S, gosh, what's going on today? S 3-phase Y would be 3. And now, so this is me remembering to multiply by a factor of 3 because I'm dealing with a 3-phase load. Since I know what my current is, the magnitude of the current squared times the impedance. That's our alternative relationship for when we only know the current and the impedance of our quantity of interest, right? So that would be 3 times 1.894 amps RMS squared times 40 plus J 15.08 ohms gives me 460.019 with an angle of 20.656 volt amperes, or 430.447 plus J 162.275 amperes. And from this, Q3 phase is just 162.275. The imaginary part, right? So part B, we want to find the average power per phase absorbed by the transmission line. So knowing what we know, how might we determine that? Cosine of what? So the complex power that we have here is the power absorbed by the load. And we're looking for the power absorbed by the transmission line. But we can easily see that our phase current through our load is the exact same thing as the line current flowing through the transmission line. So I would argue for part B, we could say that IAA is exactly equal to IAN, which was 1.894 with an angle of negative 18.742 degrees amps RMS. And so SW, only one phase, and maybe I should write that. So one phase W would be the magnitude of IAA squared times CW, or 1.894 amps RMS times 10 plus J 1.88 ohms. And actually, we don't even need to do, well, never mind. I don't want to get too confusing. But since we're looking for the average power, we could just multiply by the real part of the impedance, and that would be our answer anyway. But just for the sake of argument here, I need to do some math. 109.507 over 3. 36.502 with an angle of 10.674 degrees amperes, or 35.871 plus J 6.761 amperes. And so the per phase average power is then 35.871 watts. All right. So I think I got enough room to tuck it in right here. What we want now is the power factor at which the source supplies power. Pardon? Okay. So that is absolutely one way to do it, and I think that's probably the easiest way to do it. An alternative way to do it would be we could add the power absorbed by our load to 3 times the power absorbed by one phase of our transmission line, and then say that the source is supplying that total amount of power and get the power factor that way. But you're 100% correct that we could simply take the phase angle of the voltage minus the phase angle of the current, right? So in this case, because we're wanting the power factor at which the source supplies power, the current would be this guy right here. I'm going to call this INA, which is the exact same thing as IAA and is the exact same thing as IAN that we've already determined, right? So our power factor in this case, cosine theta V minus theta I, would just be the cosine of 0 degrees minus negative 18.742 degrees, or cosine of positive 18.742 degrees. Didn't mean to scroll that far, which is 0.947. Is this a lagging or leading power factor? Why is it lagging? Because the angle is positive. All right, so we've analyzed the circuit for its complex power.
Sure. When do we convert the radians? All the time?
Pardon?
When do we convert the omega radians? Is that every time?
Omega, by definition, is in radians per second. So I'm not sure that I fully understand your question. Okay, yeah.
And another one. So when we have phasors, how do we compare their sizes? Sometimes when I'm subtracting from another one, I don't know if I'm doing it right. I don't know if the answer is bigger or smaller than that.
Right. So that is hard to tell because so you might do a subtraction and find that the magnitude of the thing that you're getting is larger than the magnitude of either of the other quantities, but you'll find that the phase angle is wildly different. So it just is what it is. I mean, you can't really tell just by visually looking at it. The only way that you could tell whether or not you did it right would be to do, have you ever had to do like graphical combination of vectors?
Yeah.
That's, yeah.
Yeah, because like some problems I do like current division.
Mm-hmm.
And then I think the other side you can just subtract that total, right?
Sure.
And then I don't know, right? I don't know.
You have to, yeah, these complex numbers make things tricky like that. You have to trust in your ability to do math, unfortunately. But I think the graphical combination method would be a way to verify it. So just for the sake of argument here, if we had I might need to make this longer just for shits and giggles. Let's see. So this would be our real axis and this would be our imaginary axis. So if we had a voltage VA, let's call it 5 angle 15 degrees volts. So here is VA. And then we had VB was equal to 3 angle 40 degrees volts. So VB would be something like this. What would negative VB look like? It'd be the exact same thing, but 180 degrees out of phase. So it would look like this, right? Negative VB. And so when we add vectors together, and I'm going to treat subtraction as adding negative VB, we just add them tip to tail, right? So something like that. So this would be VA minus negative VB, and our resultant would be this guy right here. So it looks, in this case, the magnitude is shorter, and all that kind of stuff. Yeah. But if we were to add, like if we did something else where we had, let's call it VC was way out here in quadrant number 2. So let's say that I have, let's do purple. VC would be 5 with an angle of 100 degrees volts. This would be negative VC. So when I added that to this guy, my resultant thing, and I know this is getting messy. I've done a subtraction, but the magnitude of this guy looks longer than either of the two that I had previously. But it has to be right because that's how vectors work. So you can't intuitively say, 5 angle 30 degrees minus 2 angle 45 degrees is going to look like 3 angle something, which is not how it works, right? You can't just subtract the magnitudes from each other and figure that's a reasonable guess, because it's not. That has nothing to do with it. The correct magnitude arguably should be something around square root of 5 squared plus square root 3 squared, because that's how complex numbers work. So, all right, we got 20 minutes left. Do you guys want to try to work another problem or save it for Thursday?